Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, please consider subscribing because you're in the right spot. That said, let's get into the current video. I'm going to give an overall summary of the volume formulas for solids of rotation that you will encounter in your Calc 2 course. I'm not going to present the exact formulas. I'm not going to present any examples. I'm just going to give you an overall view of the components of each of the disk method, the washer method, the shell method when I rotate across the x-axis or the y-axis. Because a lot of times what you'll find in that course at that stage when you're learning these is it's not so much the integration that is the challenging part, although that could be challenging. The most important part is distinguishing between what method, and then within that method, whether I'm rotating horizontally, vertically, do I have a hole in the middle, do I need washers, do I need shells, what functions do I use, what equations do I use, what components, what variables, what limits of integration. That's sometimes most of the challenge comes from that part. So let's go ahead then and take a look at each one of these. For the disk method, remember what that means is I'm decomposing this object into a stack of disks, whether I think of the stack going horizontally or vertically. And again, there's no hole in it. A hole will apply to the washer method or to the shell method. Now, let's say that this stack of disks are going along the x-axis. In other words, I rotate this graph, the area under the graph, around the x-axis. Well, notice that the disks will be stacked in the x direction, and so I can think of that for within my limits of integration. For each x value, I'm counting one of the disks. That means that I'm going to integrate with respect to x. I'm integrating with respect to the orientation of the disks. If the disks are stacked in the x direction, I'm going to integrate with respect to x. Therefore, the radius will be related to the function, and in this case, the function, which would say be some curve like this, will be of the form y equal to f of x. Okay? Now, if I take a similar idea and I take an area and I rotate it about the y-axis, notice that the disks then would be stacked vertically, meaning that I would have for each respective y value a disk for each y value. That means that I'm adding the disks in the y direction. I'm adding for each y value. That means that my integral will be with respect to x. I'm sorry, excuse me, with respect to y, not x. And in that particular case, what is my radius going to be? Well, the radius is the distance from the axis of rotation to the point on the graph. But if everything in this integral is with respect to the variable y, then my integrand has to be with respect to the variable y. So I have to take the equation of that graph and I have to convert it to the form x is equal to g of y. Remember, everything that's in the integral has to be related to the same variable. Everything up here has to be with respect to x, everything here has to be with respect to y. If I'm originally given like y equals x squared, but I'm still rotating about the y-axis, I'd have to take that equation and solve it for x so that I could get it in the form x is equal to g of y. Okay? In the other case, where I'm constructing this volume of a solid of revolution formula and I notice that there's a hole in it, then it's going to come into one of the following two categories, either the washer method or the shell method. These both account for a hole in the middle of your three-dimensional object. Generally speaking, if I have two functions, I'll use the washer method. If I've got one function, chances are I'm going to use the shell method. Now, that's not always the case, because if I'm rotating, say, one function, the area bounded by one function in the x-axis about, say, a horizontal line, y equals -4, I may have to use the shell method. It just kind of comes down to whether or not I can basically solve for this expression right here. But again, you kind of have to make that judgment call based on the functions or function that is presented. But let's go through the differences. Washer method. If I'm rotating about the x-axis, then I have a washer for each x value. Therefore, my integral is going to be with respect to x, because I have a washer for each x value within the range of the limits of integration. My upper function is going to be my outer radius. My inner function is going to be or lower function is going to be my inner radius, okay? Similarly, if I rotate across the y-axis or about the y-axis, I know that my washers will be stacked vertically, so counted vertically. The vertical axis, of course, is y. Therefore, my integration variable will be y. In this case, my outer radius, I'll call it the rightmost function. So up here it was the upper function, so in other words, the graph that's farthest away from the x-axis, and the inner function or the lower function is the one that's closest to the x-axis, whereas down here, the outer function would be the one farthest away from the y-axis, so visually speaking, we'll say it's the rightmost, and then the inner function, the one that's closest to the y-axis, would be the leftmost function. So just kind of visually speaking, here it's the higher, here it's the one that's farthest to the right. And of course, in this case, since I'm integrating with respect to y, I have to convert all of these functions here to the form x is a function of y. If I go over to the shell method, again, my shell, if I rotate about the x-axis, actually, let's start down here with the rotation about the y-axis, because I think this is the more natural one to discuss. It's probably the first one that you will see. So let's say I rotate about the y-axis, I'm going to use the shell method. So I have this sort of nest of, say, well, shells, of course, but like, say, like nest of like cans or like soup cans or something that are getting progressively, say, taller or shorter, whatever the case may be, would have got this nest of soup cans. Now, the idea is that let's say I have a can that is right here, or a shell that's right here, and then I take a bigger one. Notice the idea is that for each x value, I'm going to have one shell. That means that the variable of integration is going to be x because I have a shell for each x value. And the radius is, of course, the radius of the shell here is going to be from the axis of rotation to the outermost portion of the shell. Therefore, my radius is going to be related to the independent variable x. And the height is going to be related to the function, which in this case would be y equal to f of x. Now, if I go to the case where I rotate about the x-axis, notice over here in the disk and the washer method, sort of the easier one to think about, or the one you're probably first introduced to, is by rotation about the x-axis for the disk and the washer method, because everything's with respect to x. Down here, it's rotation about the y-axis that I have with respect to x. So this is probably the first one with the shell method that you're introduced to. Now, if I look at the shell method rotating about the x-axis, again, let's put sort of like a typical shell in here. Okay, notice that the radius, which is the distance from the axis of rotation to the outermost portion of the shell, is going to be related to the independent variable y in this case. So radius is related to the independent variable y. And then, of course, since I'm expanding in the y direction, I've got a shell for each y value, so my variable is y. My height, which is also going to be related to a function, or in other words, the graph, has to have the form x is equal to g of y. So I might have to do that conversion. So again, I hope this provides a sort of a useful summary for all of the different volume formulas. In subsequent videos and previous videos, we will go through examples illustrating each one of these 6 scenarios. Also, additional videos where we will do, say, the washer method, where I rotate about a non-x or y axis, where I rotate about a vertical line or horizontal line. So we'll analyze each of those examples in other videos. Thank you for watching, and please consider subscribing.